The last practice problem for vector addition is upon us. We started with a displacement, then we did another problem that was velocity, and this time we're going to do forces, because forces are vectors also. Forces have a magnitude and a direction. So let's look at a force problem doing vector addition. So again, this is continued notes. You don't have to keep writing continued, but I want you to know what we're doing here. Prac, prov, vec addition, right? Okay. Number 3, we're doing number 3. So you're continuing on the set of pages I gave you to do these problems. They take a lot of room, right? There's a lot of steps, but here's the great news about vector addition problems. If you haven't figured it out already, it's always the same process. You follow the same steps and you're always going to get a right answer, as long as you don't make a math mistake along the way. So let's say a teddy bear is being fought over by a brother and sister, is being fought over. This is a very real situation. It happens all the time. Fought over by a bro and sis. Sis, there we go. Period. The bro pulls at, let's give it a good amount of newtons, 500 newtons, 25 degrees, let's say south of west. We haven't done a lot of souths and west stuff, so let's get that in there, south of west. The sis, I know you guys are thinking, oh, let's find out if he's going to be misogynistic right now. Let's see if he says the sister pulls head. Yeah, sure, she's a big sister. Maybe she wants the teddy bear more. She's going to pulls with 700 newtons. Let's say that she's pulling 40 degrees. We'll say east of south. Yes, that would be a good one. East of south. So these are our two vectors. And for the first time, you're seeing two angled vectors in this problem. You're seeing the brother doing this and the sister doing this, but we have, anytime you see these angles and these bearings, you know you're dealing with an angled vector, obviously, right? So when I'm dealing with two angled vectors, typically what I like to do, I'm going to kind of break rank a little bit here and change the way I approach this. Normally I draw my three vectors head to tail right away and get to my resultant. Here I'm going to take a moment to draw each vector by itself. Okay, just so I can make sure that I really get the angle and the bearing correct. So let's start with the bro over here. What I want to do is draw a little XY axis to get myself going correctly, right? This would be north, this would be south, and what is that? That's to the left, that's west, and this is east, right? So he pulls, now we already can see we're in which region. We're in this region here, right? And he pulls with 500 newtons. Remember, 500 can be however long you want it to be, right? Once you set up your 500 though, the 700 length has to be based upon that 500 length. So we are of who? We are of west. We're going to start our pen on the west and we're going to swing how many degrees? 25 degrees south. So we're going to start on the west because we are of west. I am of the west and I'm going to go 25 degrees, maybe like that. That's about 25 because we were also swinging south. You can see we weren't swinging north, we were swinging to the south. So right about there, I think that is my angle, and maybe that much is 500, right? We don't have to go overboard, that's fine. And this time we're not going to write delta x, and we're not going to write v for velocity, we're going to write F for force. So my F1 is 500 newtons. Yeah, 500 newtons. And by the way, this is our 25 degrees right here. So we have our first vector setup. It's just a way to flesh out or to visualize what's on the paper here. And let's draw the sis over here. She's pulling on this teddy bear, sis, like so. She's going 40 degrees east of south. So this time we are actually of the south. We are of the south. And remember, that's east, that's west, that's north, that's south. And we're going to go how many degrees? 40. So tell me when. I can hear you guys saying when. That's when. Stop. Okay, that's about 40. I agree with that because that's like 45, right? So 40 is a little less. And by the way, I didn't say it, but I hope you understood it. I was swinging which direction? I was swinging to the east, right? Because we are starting on the south, we're of south, and we swing to the east of that south bearing. About there, and we want to go 700. So maybe something like, that's about 500. Let's continue on, maybe make it like that. It just has to be bigger, not too much bigger. You don't want to make this arrow double the length of that because that would be 1,000, but this will be called F2 at 700 newtons. And by the way, don't forget we started on south, swung to the east, so our angle is actually right here. It's one of the #1 mistakes students make. They'll put the 40 here. They'll even put the 25 here, knowing that, they'll make silly mistakes like that. I've seen it time and time again. It's very important. You start on the of direction. Start on the of direction and swing to the other bearing. So you start on the west, you swing to the south, and in that swing that you made, that's where your angle goes. In the swing that you made, that's where your angle goes. So now we actually have a good looking picture here. And what the heck, I don't want to waste these vectors. I'm going to use these vectors for my teddy bear. Here's my teddy bear. He's being tugged on like this, poor teddy bear. Right there's his ears right there. And right, there we go. He's being pulled, poor guy. There we go. Yes. Oh, those darn kids, they're going to rip that teddy bear, right? Well, actually what's going to happen is they're both pulling like this. The teddy bear is probably going to go this direction. Let's be physical for a second. Let's stop being so mathematical for a moment, right? If I pull like this and like this simultaneously, doesn't the resulting force go something like that? Yes, it does, right? It would go something like that. So that's kind of what we're looking for our answer. Now, if we're going to handle this like we've handled the last two problems and every other problem, we're going to take these two vectors and put them head to tail. And there's nothing wrong with that. We could certainly do that. For those of you who are ready for a more intuitive approach, listen, this is for you. You could just find the components right here for this guy. And for this guy, you could just find the components right here. Then you could take your two x's, and it looks like they're going opposite. You'd subtract them. You take your two y's, and what would you do with them? You'd add them because they're going the same direction. So you don't really need to go on to the next step I'm about to do, which is to draw a head to tail diagram. Okay? That's for those of you who are feeling like you really understand this process. And for the rest of us who just want to make sure that we're keeping the same steps each time, which I completely get, and it's a good idea, let's draw both of these vectors together head to tail. So I'm going to translate this vector down here. There's my little axis, right? And it looks like I was doing about that much, right? And there's my 25 degrees right there. Blow that up for you guys. And I'm going to call this F1. Now I'm going to put the F1 here because I know it's going to get in the way if I put it up here. So I'm going to put F1 down here, 500 newtons. And now what you're going to do in order to make sure you don't mess up drawing this vector over here, put a new little XY axis right here so that you can set this one up correct. And this one would look something. My angles might be a little bit off, but it's okay. It'll still work out as long as you try to get the lengths relatively correct and the angles aren't too far off. So I'm going to zoom out. That is 40 degrees, and that is 25 right there. Okay, remember, draw a little XY axis. Once you draw this one and you want to put the tail of this vector on the head of that one, you need a new little XY axis to help you locate the directionality and put that 40 degrees in, right? So you have your reference angles. Here's our two vectors, head to tail, and by the way, I should say that this is F2 at 700 newtons. So really, all of that said, all I did was I took these two vectors and and put this one over here and drew a new picture. That's it, okay? Now, again, the difference with this problem from the other problems is you have two angled vectors. That means right now, we need to break this one into components and we need to break this one into components. This is not purely in the X or Y axis and neither is this one, but both at angles. So I need to start at the tail of the vector. I'm trying to break into components, this guy, and starting at the tail, I need to move to the head. How do I do that? By going up, down, left, or right. Which way am I going to go? Well, it should make sense to go to the left. And from the left, I could head which way? Down. And those two components would take the place of that 500 Newton vector that's angled. These are the components, the X and the Y of the 500. So I'm going to call this one F1X, and I'm going to call this guy right here F1Y. All right, so let's just handle the visualization, and then we'll do the sine cosine stuff. Now this vector here, we got to start at his tail, right? And we have to move to the head. How do we do that? Could we go right and then down? Yeah, you absolutely could. The only thing is it kind of looks a little awkward because you would cross through your 700 newtons you drew, and we already put the down here. So how about instead of going right and down, which would work, we will go down, stop there, so that you can now head which direction? Right, and get to the head. And when I stop there and go that direction, see how I ensure that I get that 90-degree angle? That's also very important. Something I haven't talked about because we're not in class. I can't field a bunch of questions. In class, sometimes I kind of act a little silly and I take this way too far down. Right? If you take it way too far down, that's not wrong, but then you'd have to kick up this direction, and now you have another angled vector on your hands, and you don't want another angled vector, right? You want to stop your down at this point so that you can move right and have two vectors that are perfectly in the y-axis and the x-axis. And on top of that, you create that 90-degree angle, which is important for your sine and cosine stuff. So that was a little extra information, I know. But anyway, once again, you want to break that into components, start at its tail, work your way to the head by going down, right, done. What are we going to call this right here? We will say that this is the y piece of who? F2. This is the x piece of who? F2. Cool. And now if I can find this one, this one, this one, and this one, I have just replaced these two angled vectors, and I don't need these angled vectors anymore. So let's find these four components, all four of these. All right, so I want to show you a slightly different way on this problem. Now, the old way is to say, okay, this x component is adjacent to the 25. So I should do, and I'm going to write it up here so you're not getting confused. I should do cosine of 25 equals the adjacent side I'm looking for, which we call f1x, all over the 500, right? And then you multiply both sides by 500. This is what we've been doing in the last two problems. And you have 500 cosine 25. I want you to see something that we just wrote here, right? We say that f1x is what? 500 times the cosine of 25. And this makes a lot of sense to me because look at your subscript here. Look at your variable. It says f1, the x piece. Who is f1? What is f1 worth? It's worth 500. Don't we have a 500 right here? Yeah. 500, the x component. Now the x component in this case is cosine because this side right here is touching the 25. So when I know I'm dealing with the adjacent side, I know to use the cosine of the angle. So really I can apply this type of thinking and shortcut every single one of these. This would be 500 cosine 25. This, look at what this says. This says f1, the y piece. f1, who's f1? 500. The y piece. Well, this means either sine or cosine, right? And so do you agree that this side is opposite from the angle? Yes. And sine deals with the opposite side. So I'll say sine of 25. Remember, when I write so and ka, if I'm dealing with an adjacent side to the angle, who should I be using? Cosine. If I'm dealing with an opposite side, which the side was opposite, I should be dealing with who? The sine of the angle. So what I'm trying to get you guys to realize is if you label your vector correctly, it leads you directly into an expression, mathematical expression, that can get you the answer. 500 times the cosine of 25. F1 is 500. The x piece is adjacent, so I should be using cosine. I hope that makes sense. Let's apply that thinking down here. Right here, what does it say? It says F2x. Well, who's F2? F2 is the hypotenuse, 700. X. Now, look at this though. I don't want you to start thinking that x always means cosine. Up here, x meant cosine, right? But here, isn't our x piece opposite from the 40, right? So if we're opposite from, who are we dealing with? Sine of 40. And there you go. It's already set up for you. What about F2y? Well, F2y, it says F2, so let's write F2. What's F2? 700, right? The y component. Well, this y component is adjacent to the 40 because you can see it's physically touching the 40. And if we're dealing with adjacent, we're dealing with which function? The cosine of 40. So if you like this shortcut, and I do, I really like this shortcut because I do not like doing this over and over again for every component. Now, please understand, I'm completely fine with you doing this over and over again for every component. If you like doing it the way your geometry teacher taught you or your math 2 teacher, whoever taught it to you, right? But I like this shortcut. Because really, this is the most tedious part of the problem, in my opinion. So I'm going to do a fast set of calculations. I'm going to do 500 times the cosine of 25, and I get 453.15. I'm just going to leave it at 453 newtons, right? You're going to see me round a lot on this one. 500 times the sine of 25 would give me 211. You can see I'm aggressively rounding here. Normally, I would like you to use that 10th, right? 211.3, but I just want you to get the concept here. And since our numbers are big enough, it's okay that we're rounding to the nearest ones place. 700 sine 40 is about 450, right? 449.95 would be 450. So this guy down here is 450 newtons. And then 700 cosine of 40 would be 536. So this part right here is 536 newtons. That's the F2y, right? The F2y. Cool. Very good. We're ready for the next step. I just got all x's and all y's so I can get rid of thinking about these two angled vectors. I don't care about them. What I do care about doing now is summing up or adding up all of my forces, my F's in the x-axis, and adding up all my forces in the y-axis. Now let's start with the y-axis just because I think it's easier. Aren't both of these heading south? Aren't both of these forces pulling south? Yes. So I'm going to say 536 plus my other south, which is also same direction. So you add it. And let's get an answer. You'd have, what is that, 747? I think it's 7, yeah, it should be 747 newtons south. Now that's not north, right? That's a newton. That's the unit of the force. Let's look at the Fx. Who is stronger? Man, they're almost the same strength, right? But who is a little bit stronger? Isn't this direction a little bit stronger? So the brother, even though he was pulling, excuse me, he was pulling with less force, more of his force was acting in the x-axis and more of the sister's force was happening in the y-axis, wouldn't you say? So actually the bit of x that she has, 450, is less than his x, 453, right? Because they both pulled at different angles. You can see clearly that she's pulling harder in the y-axis than he is, though. She pulls with a lot more at 536 than his 211. But the point here is that he's pulling harder in the x-axis, so we're going to start with 453 newtons minus her 450 newtons. And we get this tiny little amount of newtons, 3 newtons. Which direction? To the left, actually west, right? 3 newtons west, 474 newtons south. Let's take these two answers, which we should know at this point are the x and the y component of our final vector. Final vector? You didn't even draw it. You're right, I didn't. Let's see what it looks like. Doesn't your final vector look something like that? Isn't that my FR? My result should go from the tail of the first vector to the head of the last vector, right? It's the tail of that green vector, boom, boom, boom. So ultimately, the teddy bear is being pulled down really hard and a little bit to the west, right? A little bit, a lot south, and a little bit, a tiny bit west. So at this point, you know what I like to do? I like to draw a whole new triangle. I'm going to try to keep it on this page. I encourage you to use more space, though. All right, I don't want you to crowd your work and then not understand it when you look back. But this is what's going on. I have a ton of force happening south, right? I have 747 newtons, as a matter of fact, happening south. And I have this tiny little bit, and I'm going to have to over-exaggerate it. 3 newtons. 3 newtons acting west. Notice I put the head of that one on the tail of that one. That means my FR would go from the tail of the first vector to the head of the last vector, right? So you put these two components head to tail, and they create a resultant that goes from the tail of the first to the head of the last. That's my FR. Let's also handle this right now. Where are you supposed to put your little XY axis? At the tail of the resultant vector. At the tail of the resultant vector, put a little XY axis, just like that. And you can clearly see I am in the west-south region of that compass, right? Oops. Okay, so let's find that FR. Yeah, let's find that FR using that drawing and staying on this page. FR would be equal to the square root, right? This squared equals that squared plus that squared. Take the square root of both sides and you get FR equals the square root of 747 squared plus 3 squared. Let's find out what we get. $747. And you might see that and say, oh, I must have done something wrong. No, you didn't do anything wrong. Here's the deal. That's such a small amount squared. I mean, that's only 9, right? Compared to that, I mean, that is huge when you square it compared to that. So that little 9 is like hardly a dent at all in this math operation. And so you basically get the same answer as the south vector because let's face it, your west was so tiny in comparison. So I'm going to write here, it's 747. You might think, okay, south, done. And you're not wrong. The degree is going to be so tiny, it's ridiculous, but we still should go through the process of finding that degree anyway. You're right, it's mostly going to be south, but anyway, let's find that angle. So at what angle? What is this angle right there, that theta that I just drew in? Remember, I picked that angle instead of this angle. I don't want that angle because it's not inside the triangle, but this angle is. So let's find it. We would say up here, I'm going to say theta. I'm going to skip a step here. I believe that you guys are getting better at this. Theta is the inverse tangent of opposite 3 over adjacent 747. 3 is the opposite side, 747 is the adjacent side. Let's find out what that is. Second tangent of 3 divided by 747, 0.23 degrees. That's not even a full degree. It's 0.23 degrees. 0.23 degrees south of west or west of south? South of west or west of south? You are of who? Your angle touches who? You are of the south, and you have to swing which way from the south? West. West of south. That's your answer. So it looks like this teddy bear is doing this number right here, right? That teddy bear is being pulled that direction. Hopefully he has good stitching on his arms and he will not be ripped apart. Okay, that was the last example problem. You got to see a displacement, a velocity, and a force vector addition problem. You can see this process works for any type of vector. Really, the only difference is I didn't call it delta x, I called it f. Or if it's velocity, you put a v there. But everything else is exactly the same. All right, have a good one, guys. Talk to you soon.